This is Unit 1, Fundamental Definitions. The reason why we start with fundamental definitions is to make sure that when we go through the entirety of this course together over the next few weeks, the foundational terminology and concepts and buzzwords in use across the industry are in line with what is found in academic literature, and to ensure that together we are on the same page when we use this terminology throughout the course. You may have already seen course introduction as part of the free preview video introducing the contents of the course. Today we'll begin with section 1.2, what is data science? Subsequently, unit 1 deals with what is machine learning in section 1.3, what is artificial intelligence in section 1.4, and finally, business perspective on AI in section 1.5. Let's begin. What's data science? And even before that, what's data? What does it help us achieve? What is data analytics, data mining, and data science? First things first, what's data? Where one source suggests that every day over 400 million terabytes of data on estimate circulate the internet. And this can be of a variety of types. Structured data that's comprising of files, databases, tabular data, so to speak. It could be text-based documents data or images, which we would call unstructured data. And then everything in between those two, which we can put in the semi-structured type. So all around the world, businesses and organizations are keen to find patterns and meaningful information in this vast amounts of data that's available to them and us all. The reason being that there are hidden patterns in data, which once discovered and made meaningful, can then be used to design campaigns and execute those campaigns to optimize existing strategy or devise a new strategy. And it can also be used to create new products and much more. Having set the premise that there is an abundance of data around us, the fact that we need to extract these patterns from data to make it more meaningful, we will need some kind of a method. We know that science, it's a systematic study of structure and or behavior of phenomena. These phenomena are part of the world around us, which could either be the natural world or even the man-made world. And the scientific study, this systematic study of structure and behavior, is conducted through observation, experimentation, and testing theory or hypothesis against collected evidence. On the right hand, you see there is the structure, and a stimulus is applied to this structure, which generates a response from this entity. And this leads to an ability for scientists to observe its behavior in relation to the applied stimulus. Let's take this with examples to make it more concrete. A structure of a friend's network on social media or even in real life. Another example, which is a bit closer to formal uses of scientific method and studies, is creating a new drug or medicine and then understanding and analyzing the behavior of this new medicine in the treatment of a disease, where you may take a cohort of patients and volunteers, create control groups, apply the stimulus with the new medicine to one of the groups, and compare the two groups' behavior and how they respond. So, putting the two together, remember we said science was conducted through observation, experimentation, testing of theory or hypotheses. So, in data science, we take data on observations, which may include quantitative data or qualitative data. Quantitative data has measurements and readings. For instance, it could be the height or the weight or age of a particular person or a group of persons. And qualitative data is attributes. So, for instance, eye color as well as hair type, etc. Now, these observations may also be time based. So, you've sampled these over years or months, or they could be for the same persons or group of persons over time. They could also be groups based, so you can compare the means of groups. So, you take a set of observations in one part of the world, a set of observations in another part of the world, depending on the kind of study that you're conducting. The second stage of the scientific method after observation we saw was experimentation. An experiment is designed in such a way so that we can discover something that is unknown hitherto. For instance, some kind of a hidden pattern or relationship. And we take the observed data and we use this to either verify or refute our hypothesis in experimentation. So, what's a hypothesis? A hypothesis is a proposition that seems true but needs to be validated using data within the context of an investigation or a set of experiments. And this validation can be done using some kind of a threshold or criterion for validation. So let's take this with an example as well. Let's say that I make a hypothesis today and state that cars are expensive in Pakistan. Now I need to qualify this statement and I need to verify or refute this hypothesis by looking at some observed data and using some kind of a threshold or criterion for validation to prove that this hypothesis is correct or incorrect. So let's say, based on some surveys or questions and answers and interviews with experts in Pakistan who deal in car sales, I arrive at a threshold, an agreed threshold of $3,000. So we say that anything above $3,000 is indeed expensive when it comes to cars. Now we collect some sample of data for a number of cars. We can derive a variety of different factors such as the brand, the make, the model, the year, and use this sample with the criterion for validation, my threshold of $3,000, to verify or refute this hypothesis. If most of the cars end up below this $3,000 threshold, then my hypothesis would be incorrect. Another example could be cars are more expensive in Pakistan compared to cars in India. In this case, I would have to take two observed samples, one from Pakistan, another from India, to be able to compare the two and refute or validate the hypothesis. So, moving on to the third stage, how actually do you test this theory or hypothesis? Well, you need to determine that there's enough evidence in the data sample to draw conclusions about the population. Because remember, you can't take all of the population's data to include in the study. So there's always a need to ensure that the sample is representative of the population. We should be able to make some kind of probabilistic statements about population parameters based on the sample. We should always use competing hypotheses, so the null hypothesis and the alternative hypothesis. We should be able to use statistical inference to decide whether the data at hand is sufficient and supporting the hypothesis. And there are various statistical tests that we use to ensure that we are validating or refuting our hypothesis correctly. Examples of these tests include ANOVA, analysis of variance, or the right-tailed and left-tailed test, which is the one-tailed test. If your threshold is not a range but a point. So in our previous example, $3,000 would be a one-tailed test because we're looking to see whether anything is more expensive, whether the cars are generally more expensive than $3,000. A two-tailed test where you might have an upper bound and a lower bound where you're checking something and refuting or validating a hypothesis. And there are many other tests. So bringing it all together, then data science is observation, collection of data, which means that we will prepare the data for analysis as well, which might mean that we have to clean the data, fill in missing values, merge data sets together to create new views, and pre-process it so that it's ready to be ingested by statistical methods and machine learning algorithms. Observation may also include visualization of data to be able to formulate hypotheses and manually and visually look for patterns that may be visible directly. Exploration of data is also another part of observation. This is where you ask questions and observe. Again, from a business domain perspective, having expert knowledge allows for a formulation of hypotheses that is deductive or top down, coming from the business, rather than inductive or empirical, that is data driven, what's seen in the data. It may be a combination of both of those approaches. Next stage then being the testing of formulated hypotheses, which is where we are using the statistical tests and evaluating our results. The third stage becomes experimentation, because now that we've validated the hypothesis, we want to be able to predict or forecast something for the business to be able to be proactive rather than reactive to some phenomena. So in this case, we bring in statistical and mathematical models, machine learning algorithms to be able to create some kind of a model or solution which will proactively predict or forecast, let's say, some quantity X. Of course, once we've developed the model, we have to evaluate whether this model is any good, whether it's performant, and then we might even have to iteratively optimize it. And finally, of course, in real world scenarios, we would have to deploy these models as well so that the operationalization of these within business processes can be made complete and business users and end users can actually start reaping the rewards and benefits that are being generated through the extracted meaningful information using data science. Formally then, within a data science life cycle, starting from the top right, we have business problem understanding. Following that, we have data collection and understanding, data cleaning and preparation, data visualization and exploratory analysis, hypothesis testing, machine learning, model evaluation, optimization, deployment and operationalization. So business problem understanding is where we essentially meet with the business to understand what kind of problems they have, select one of those, collect data on it, understand how it manifests in data, ask questions, understand the process further with the business experts, move into data cleaning and preparation, start visualizing and exploratory analysis, and present the outcomes again to business users to be able to formulate hypotheses with them or to refute and validate the hypothesis they've already come up with. Here we formally test the hypothesis using statistical methods and tests. And once that's validated, we may be able to get funding to push it through actually developing a model using machine learning algorithms to predict or forecast. Once we've developed one or more models, we evaluate the results and optimize those, and then we deploy and operationalize the solution for the business users to actually start using the solution to address the business problem with the solution that's been developed. So in conclusion, data science is a confluence of several fields. It brings together, on the one hand, computer science, maths and stats, as well as business knowledge. Putting business knowledge together with maths and stats, we have traditional research methods. Putting business knowledge and computer science, we have software development. That's an existing field as well. If you put computer science and maths and stats together, we have machine learning. And putting all of these 6 fields together, we have the confluence in the middle, which is what data science is. So it's essentially understanding some kind of processes or problems that the business are dealing with to create a software solution for it with computer science that they may already be using and is insufficient. And they may already have a research department using stats and maths to actually find out solutions on their own. Data scientists can come and help this to validate the hypotheses with a lot of data, and using machine learning, build models that will automate this solutioning or give them some prediction and forecast to suggest and facilitate business users. This essentially extracts actionable insight from data, which helps improve decision making that is well informed and timely. Let's take another pause here and bring it all together. Let's say there is a business. And this business has its own proprietary data that it's been collecting for years. This might include structured data, documents, databases, repositories of documents, data on the cloud. You might even have unstructured data such as audio recordings and video recordings, for instance. This is the entirety of its proprietary data, let's say. Now, the business, of course, having its own org structure, might have several business units that have all contributed to and hold this data in different silos, for instance. And we need to find out how to bring relevant data together from a data science perspective to build some kind of an AI application. Let's say the business already has a business intelligence unit that is working on formulating hypotheses by exploring data, creating business charts, and using this data to some degree, consuming it for the business in reporting. So this exploration might lead to bar charts, column charts, line charts, line plots, even pie charts, for instance. Let's say the business leaders or managers or colleagues from the technical departments, the research and development departments already have some deduced hypotheses. This could be either deduced or deductive, let's say, because they have experiential knowledge, or these could be inductive, that is, generated by exploring the data sets as the business intelligence unit has been doing in our example. So there could be a number of hypotheses that they already have. A hypothesis like cards are expensive in Pakistan, as we saw earlier. In this case, the business could have a hypothesis saying that if we make X, Y, and Z changes to our product, it will sell more, or that the product is selling more in a particular region in the world because of A, B, and C reasons. And all of these hypotheses could be put to the scientific method, as we saw, taking an observed sample of data, testing it, using statistical tests to validate and refute. And we saw very crude examples of this earlier on, just to make a point that the data collected needs to be representative of the population, and then the result should be statistically significant for us to say that our hypothesis is correct. Let's assume that after testing this set of hypotheses, the business reaches a conclusion that only one of the three hypotheses, or the set of hypotheses that they have, H2 in this case, is valid, and therefore the business signs or approves sponsorship and provides funding for this hypothesis to be taken forward into a proof of concept prototype where machine learning algorithms will be used to develop a model that can predict or forecast or provide some kind of a proactive, ahead of time output that will help the business. So we'll take this proof of concept prototype through the data science lifecycle that we saw earlier, through all of those stages to developing a POC and then a minimum viable product, an MVP, which will be packaged up in some kind of a dashboard or an application that is passed back and handed over to the business users so that they can incorporate this into their business as usual. And this MVP feeds back data into the proprietary data set of the business. So we complete section 1.2, what is data science, on this final slide, which is examples of data science applications by industry, just to give a flavor of how data science is used globally. We have education, governments and education departments using data science to plan infrastructure upgrades and development, optimize education policy. You also have adaptive personalized learning for students at schools and universities. Then data science can also assist in evaluation of performance of students. In healthcare, radiology images are being diagnosed using computer vision, deep learning, and data science. Patient pathways optimization, so when patients are encountering the healthcare system, how do they move through the various stages to reach where they need to be treated optimally. Bed utilization to ensure that the resources of the hospital are optimally used, as well as chronic disease vulnerability or predicting the onset likelihood for a population to have a certain chronic disease. This is so that the government, for instance, can make proactive policy shifts and changes to bring the healthcare system from being reactive to proactive. Similarly, in financial services, data science is used to detect transactional fraud using machine learning or suggest and recommend different types of products in banking to customers who would be likely to opt in. This is done by looking at the customer base and segmenting it to identify those customers who would be more likely to opt in based on their profile, and loan approvals based on credit rating or risk score. In energy, you might have predictive maintenance of power generation, machinery, turbines, smart meter modeling, or incentivization to reduce energy consumption in the residential or commercial markets, and optimization of solar throughput, for example. Finally, in real estate, you might have house price prediction, which is a very typical example that's used in machine learning courses for students to understand how a machine learning model is developed. And later on, you will see we will be using the same example when we start talking about machine learning in this course. So this brings us to the end of section 1.2, and I'll see you in the next section.